For the rest of our day, we're going to talk about section 8.4. And 8.4 is going to be your favorite. What's your favorite thing to do besides fractions?
Graphing.
Really? Oh, this is easy graphing though. This is as far as we go in graphing. Isn't that nice?
Dividing fractions.
No, it's word problems. That's your favorite.
Hey, that's the only thing I don't like about him.
Why, Mr. Leonard, are you such a jerk? Well, it's my job to be a jerk. I love my job. We're going to talk about something called variation, and then we're going to do some problem solving. Of course, problem solving means word problems. Now, fortunately, in this section, most of the word problems are very, very similar. So I can really tell you how to do every single one of them, which is good. So variation and problem solving. Oh my. You know, there's really two types of variation. We have something called direct variation, and we have something called inverse variation. You deal with these on a day-to-day basis. You're going to understand what these concepts are. We just have to take those concepts, run with them, and apply them to some word problems. That's basically the idea of this section. We're going to try to accomplish some direct variation first. I'll give you a couple examples of direct variation before we go any further. I'll give you a mathy explanation in just a second, but here's what direct variation means to you. It means if one thing goes up, another thing goes up. For instance, how many people have jobs in here? You guys work. Good, okay. Most likely you get paid by the hour, right? If you work more hours, what happens to your pay? So if you work more, you get more money. That's why people work, right? To get more money. If you work less, what happens to your pay? It goes down. They're tied together. One goes up, the other goes up. One goes down, the other goes down. Does that make sense to you? That's direct variation. The more you do one thing, the more you have another thing. And the more you have one thing, the more you have another thing. They're tied together. They both go up, and they both go down at the same time. It's not like this, right? So, another example is like Disneyland. The more time you spend at Disneyland, the more fun you will have. Actually, that might not be true. It might be the more time you spend, the less fun you have. No, let's just pretend the more time you spend there, the more fun that you're having. Yay, we're having so much fun. The teacups and you throw up. Oh, it's fantastic. That's what direct variation means. It means as one thing goes up, another thing goes up. Or in terms of x and y, as x increases, y also increases. So if y varies directly, it's another way we can say direct variation. If y varies directly as x, you can hear that a lot. If y varies directly, the key word there is directly. If y varies directly as x, right there that's tied x and y together, okay, in a very specific relationship. It says, as x goes up, y also goes up. So if y varies directly as x, I'll say it this way. Y goes up when x goes up. Or y goes down when x goes down. They're tied together. Fortunately, in variation, the formulas are really quite simple. They're not anything like extravagant. Here's how direct variation will always look. It simply has your first variable, which is tied to your second variable. Now, I do have to make a point here. We're not always going to be using the letters x and y. This could be dollars and hours, couldn't it? The dollars you make varies directly as the hours you work. Are you getting the picture there? So we could have dollars and hours, so D and H. We could have D and H instead of Y and X. We could have that. So the Y and X are really arbitrary, they don't matter that much. It's the idea that one thing is tied to the other, and as one thing goes up, the other thing goes up. So Y varies directly as X means Y equals something times X. I want you to look at this. If you're multiplying something, won't this go up as this goes up? Say k is a constant. Okay, k doesn't change. So k is a constant. It's called the constant of variation. And we'll be finding k in all of our problems. If k stays the same and you start raising x, notice you're multiplying this number by x. If you start raising x up, y's got to go up. This would be exactly the case of an hourly employee. K is going to be your hours, the dollars per hour that you make. So you guys make what, $10 an hour maybe? 9, 8, would? You would? Okay, I'm not going to ask you how much you make there, Daniel. We'll say that you make $9 an hour, okay? K would be 9. If you work 5 hours, you get $45. Did I do that math right? Okay. If k goes up to 10 hours, you make $90. Does that make sense? If x goes up even more, you make even more. So if your hours go up, your dollars go up. This is direct variation. Doesn't necessarily have to be x and y, but that k, that will always be in your problem. That will be a constant of variation. Let's do one example and then we'll call it a day today. Suppose y varies directly as x. That's the key statement. Suppose y varies directly as x. That right there tells you how to set up your equation. If y is 24, when x is 8, what I want to do is find k and set up the direct variation equation. Okay, that sounds all pretty complicated if we don't know what we're doing. But let's go through this piece by piece. First thing, does it say direct? There's going to be two words. There's direct and indirect or inverse. So we're looking for either direct or indirect or inverse. Now, I've covered those two things, so naturally this is going to be direct. But that's what I want you to look for. Is this direct?
Yes.
Yeah, it says directly right up there. And then we read about it. It says y varies directly as x. What that means to you is, right off the bat, if y varies directly, what it means is y equals k times x. Listen carefully, please. Please listen. Direct means k times. I'm going to say that a lot. K times. Direct means k times something. K times something. Inverse, when we get to this, is going to be k over something. So the relationship between direct and inverse is k times for direct, k over for inverse or indirect. Okay, that means divided by. That's what I'm kind of previewing that for tomorrow. But right now, when we read direct, we should be k times, not k over, k times. So we have the first thing, y, equals k times varies directly as the second thing, x. Hey, do you know how much y is? Great. Do you know how much x is?
8.
Do you know how much k is? Not yet. But we know that 24 equals k times 8, or 8k, it's fine. Can you solve for k? Yeah, it has to give you all the information to do this. If we divide by 8, that was relatively painless, right? Relatively painless. You have to do one more thing though. You don't leave it here. You have to do one more thing. You see, right now we found k. We're not done with the problem yet though, because we want to write the equation. Here's the only thing you need to do now. You go back up to where you started. Y equals k times x. Have you found k? Then all you do is take this value, plug it into that number, and rewrite this part of it. So without the 24 and the 8, you just use the 24 and the 8 to solve for k. Then we rewrite our equation. So we're going to have y equals what?
3.
How much?
3.
3 what?
X.
3x. That's it. That's your direct variation equation. So we notice direct, we set the basic equation, we fill out some numbers that they give you, you solve for k, you rewrite it. Now, the reason why we write this is because the next part of this question is going to be this. Find y when x is equal to 10. Can you do that? How much would y be? 30. Find x when y equals 20. You have 20 over 3. You can do that sort of thing. So we use this to set the equation. We set the equation because eventually we're going to answer different questions about that. This will lead us into some actual word problems later where we're working on stuff. We'll start with one of these tomorrow. That'll be the end for today. We were talking about direct variation. Can someone give me an example of what direct variation means? Remember that we're talking about something that when one thing goes up, another thing goes up. That's right. That's the example I gave you last time. Have you thought about any different examples besides hours and wages? Sure, that is direct, right? Because as your hours go up, the amount of money you make goes up. We talked about that. Anything else that you can think of?
Your heart rate.
What now?
Your heart rate, when you go faster, work out.
Sure, okay. So you exercise more, your heart rate goes up. That's pretty much tied together. That'd be kind of silly if you exercise more and your heart rate went down, right? That'd be crazy. Or if you rested and your heart just starts going boom. You need to exercise, your heart's going to explode. That'd be good for some people, I think. Just start getting you out there, getting going. But yeah, that's direct variation. It means as one thing goes up, the other thing also goes up. And what we realize is that if we're talking about variables x and y, if x goes up, y goes up. That y depends on our x, and so we have our equation y equals k times x. I made it really clear yesterday that direct is k times. You see, we're going to be talking about inverse or indirect variation in just a bit, and we're going to have k over. And that's kind of like a little preview that we talked about yesterday. Let's do one example to really get our brains kind of rolling on this stuff, and then we'll move on, okay? So this is going to look similar to the one we did yesterday, but let's suppose y varies directly as x. Right there, that tells you what type of equation you're working with. When we say varies directly, the key word there is direct. So we know automatically the first thing is dependent on the second thing. In this case, that's y is dependent on x, and we're doing k times. That's what that's telling you. That's what we learned yesterday. Let's say if y equals 20, when x is, let's say 15. What we're going to do, we're going to find k again, and then we're going to write the equation. So find k and write the direct variation equation. Hey, by the way, when we're looking at this thing, what is k?
Constant.
So, okay, so once we find it, is it ever going to change for this particular problem?
No.
All right. So you tell me, what's the first thing we might want to do in our problem here? What do you think? What now?
Find k.
Okay, how are we going to find k? Firstly, do you know what equation we're using? What's, say that louder?
Y equals k times x.
Sure, and the reason why we know it's k times, what's the key word there to represent k times? What is that?
Varies directly.
Yeah, so we're talking about direct. So varies directly, we know we're doing y equals k times x. That's good. So on the left-hand side of the room, what's our next step? What do you think?
Find what x equals?
Sure, how much is x in our case?
15.
Sure, and how much is y?
We don't know.
So let's go ahead and substitute those in. Go ahead and do that on your own and solve for k. Try to solve the case of the missing sign-in sheet. Did you guys notice the sign-in sheet yesterday?
Yeah.
I accidentally took you.
You're the man.
Send him to jail.
My bad.
You're going to math jail. It's a wonderful place full of equations. All right. Well, I'm glad you remember. Okay, let's see what happens here. So we know we have to substitute in. That's why the second sentence is even there, to give us some numbers to allow us to solve for k. So when we're dealing with direct or even inverse variation in just a little while, we're going to have one of these equations, either y equals k times x, or in the future we'll have y equals k over x. The problem is going to give you two numbers to plug in. Since we have those three variables up there, they have to give you two of them to solve for the missing one. In our case, they give us y, which is 20. Do we know what x equals? Really?
No,
I'm sorry, k. Do we know what k equals?
no.
No, not so much. We do know what x equals. That's going to be 15. How are we going to solve for k in our problem here? Sure. By what? Okay. So of course our 15s on the right hand side, they create that 1 for us and we're left with k. On the left hand side, what are we going to have? Yeah, good. So we are reducing this as well. Are we done?
No.
We're almost done. We've done the hard part. We've solved for k. However, what I told you last time is that we want to rewrite the equation because that's going to allow us to solve for any other pieces of information that we might need to find. So tell me exactly what I need to have once I resubstitute in k. What am I going to get now? Good. So essentially we're just changing this by replacing k with what we know k to be. Would you raise your hand if you feel okay with this direct variation? Would you like to see how this is applied to like a real life situation? So we're like, nah, not so much. By the way, the answer to that question is always, yes, Mr. Leonard. We're so excited to see. That's the answer. So are you guys ready to see how this is going to be applied to it?
Yes.
Oh, good. We're so excited. And the rest of it, we're so excited. Okay, good. I'm sure you are. Okay, so let's suppose we had this situation. From the ceiling, I'm going to hang a spring. Okay, so like a scale basically. So some sort of spring from the ceiling. And I'm going to put some weight on this spring. What's going to happen to the spring? Probably it's not going to go up, is it? It's going to go probably stretch down a little bit. Let's say that I take that weight off and I put a heavier weight on. What's going to happen to that spring? It's going to go even more. So would you agree that for a certain stretching of the spring, now eventually that spring is going to stretch all the way to its maximum and not go any further, right? But for a certain distance, the more weight we put on that spring, the more it's going to stretch. Do you agree? Does that fall into the category of direct variation? More weight equals more stretch. So those things are tied together. Less weight means less stretch. So we know that as the weight goes up, the stretch goes up. Let's see if we can write out a word problem, identify that it's direct variation, see if we can solve some things about it. So let's suppose that the distance a spring stretches, that's going to be a tongue twister the whole day. The distance a spring stretches is directly proportional to the weight that's attached to it. Wait a minute, directly proportional? What's that mean? What's directly proportional mean? What's the key word in directly proportional? Directly, that's it. It's the same thing as varies directly, so that's a different way to say varies directly or directly proportional. It's the key word is really direct in this case, okay? So even if you see directly proportional, we mean varies directly, it means. So the distance a spring stretches is directly proportional to the weight attached. That tells you what equation you're going to set up. Okay, the second sentence is going to tell you some numbers to plug in. The third sentence is going to tell you what to do with those numbers. So right now I'm going to take a break. I'll write more of this problem out in just a second. But I want to make sure we're understanding how to set up the equation in this case. Now, I told you last time, in the 5 minutes we really talked about this, that we don't always have to have y and x. Y and x are kind of some dummy variables. The idea is, if y varies directly as x, y comes first and x comes second. In our case over here, the distance a spring stretches is directly proportional to the weight attached. I don't have an x and a y. What are my two variables that I'm talking about here? The distance the spring is stretching, that's great. So this is one of them. And what's it proportional or directly proportional to? So weight's another one. So maybe we don't have y and x, maybe we have, what variables do you want to use? Yeah, original, right? D for distance and w for weight. So how are we going to write out the equation if we don't have y and x anymore, we have d and w? Can you tell me?
D equals K times W.
Sure. Why, ladies and gentlemen, is it d equals k times? What's that k times coming from? What word clues you into that? Good, okay, so d for our distance, that's the first thing that we saw in our sentence. So distance is varying directly, that means distance equals k times, well, whatever weight we're going to put on that thing. So that's our first part to our problem here. We need to identify that equation we're working with. Now I'm going to fill in the rest of I'm going to move this down a little bit also. Fill in the rest of our question. So d equals k times w. We got that from our very first sentence. Then it has to give you some information. Let's say a 56-pound weight on this spring stretches at 8 inches. Well, it tells you some pretty good information. Can you please tell me where's the 56 going to go in the equation we just made up? Yeah, why? Okay. And where's 8 going to go? So we could actually substitute in our 56 and our 8 for the equation we just made up. If a 56-pound weight stretches that thing 8 inches, the distance it's stretching is, well, it's 8. We don't know what k is. That's really part of this problem, times 56. I'd like to see if you understand what we're talking about here. Nod your head if you're okay getting from this point to this point. Yes. Good, okay. What do we need to do to solve for k? Divide by what? 8 or 56? Look where your k's at. We need to get k by itself. What's attached to the k? Okay, so we're divided by 56 in our case. Wait a second. Wait a second. 8 over 56, is that even possible?
Yes, you can simplify it.
It's not going to be a whole number. That's fine. We don't have to have a whole number up here. What is 8 over 56?
1/7.
Sure, we're going to simplify that fraction. We're going to get 1/7. There's nothing that says k has to be an integer or a whole number. What it says is that k is being multiplied by x if it's directly proportional or varies directly. So in our case, we get 1/7 k equals k. 1/7 equals k. Okay, we should be good at this point. What do we do now?
You're gonna plug it in. Okay.
All right. So when we do that, the d's not going to change. I know all that's changing is that k. So d equals, instead of k, I'll do the 1/7. That's what we just found, times w. Now, this allows you to solve for any other piece of information I want. So if I say, instead of a 56-pound weight, I want you to go ahead and put on, or what I have down here, an 85-pound weight. Could you figure out how much that stretches? What are you going to plug the 85 into? That's the new weight. So the idea is this. We use our first sentence, or the thing that says varies directly or directly proportional, or in the future inversely proportional or varies inversely, to set up our equation. The next sentence is going to give us two pieces of information. That lets you solve for your k. Once you solve for your k, that's setting you up with a very nice equation you can use to solve for any other piece of information. So when I do this next part, how far will an 85-pound weight stretch this spring? We can figure that out. by the way, just one more time, where's the 85 go? Does 85 go for the D or for the W? Yeah, it's definitely a weight, so let's plug that in. I have D equals 1/7 times our 85. 1/7 times 85, well, 1/7 doesn't, or 7 really doesn't divide the 85 evenly, does it? Okay. So we can write the distance equals 85 over 7. 85 over 7 what, though? What are we talking about here? So make sure we're using our units correctly. This isn't stretching feet or anything, right? It's definitely not stretching miles. It's stretching inches. 85 over 7 inches, or if you want to use your calculator to get a decimal, because typically you're not going to go, oh yeah, I just traveled 85 over 7 inches. Do you do that? I'm traveling 85 over 13 miles per hour, officer. That's how fast I was going, honestly. That doesn't make sense. So maybe translate this into a decimal for a real life situation. Do you have that down?
Yeah, 12.14.
Okay. So it's stretched at 12.14 inches. Hey, one more question. If I did this another way, let's say I asked you, what weight would it take to stretch the spring 15 inches? Could you do that? Where would you plug in the 15? And then we just multiply by 7 on both sides, and that would give us the weight that we would need to solve or to find a certain distance of stretch. Would you raise your hand if you feel okay with this problem? Setting up the direct variation. Okay, good stuff. We got direct variation. Direct means as one thing goes up, another thing goes up. As the weight goes up, the stretch goes up. There is another type of variation we have to talk about though. Specifically, we're going to talk about inverse variation. Hey, what do you suppose inverse variation means, since we just talked about direct variation?
The opposite.
Yeah, it's the opposite. If one thing goes up, the other thing goes down. For instance, this always happens to me. Well, it doesn't always happen to me, but most of the time this happens to me. If I spend more time in a casino, I have less what?
Money.
Yeah, I have way less money. And actually I have less fun too, because I have less money. So the more time you spend there, the less money you have. Right? The farther or the longer you drive your car, the less gas you have. Does that make sense? So as one thing goes up, another thing goes down. Give me an example of inverse variation. Can you think of one?
The more you go shopping, the less money you have.
Yeah, that's true too. Well, unless you just don't take your credit cards with you, which sometimes I do that. It's kind of fun to look, right? You gotta get new shoes or something. Well, not. Actually, I don't buy new shoes. Never mind, doesn't really matter. I go car shopping. I love shopping for cars. Just drive them around, free trip around the city if you like. Sometimes they let you stop off and get a Slurpee sometimes too. If they really want to make the sale, they'll let you do that. Give me a different example of inverse variation. One thing goes up, another thing goes down.
Leave your electricity on, the more you have to pay. Or the left side of the one.
Yeah, that'd be direct, right? The longer you leave it on, the more you have to pay. Okay, so we have another direct. Anybody else?
The more exercise you do, the less weight you have.
Very good. Okay, so the more you exercise, the less weight you have, unless you're just pumping iron, right? Daniel, he's seriously buff in there. But yeah, the more you exercise, typically the less fat you have, the less you're gonna have that on your body. So, they're very good examples of inverse variation. Here's the idea: with inverse variation, or in other words, we'll use some variables here. If y varies inversely as x. So the key word for us in this context is inversely. If y varies inversely as x, then y goes down as x goes up. And this is the opposite of direct. X went up and y went up. In this case, x goes down and y goes up. Or x goes up and y goes down. It's that relationship. The way we can get from direct to inverse. If direct was k times something, k times, as this thing goes up, we're multiplying it by some multiplier, it's making a larger quantity. It's making this quantity larger. In order to raise a number and have something else go down, that's going to represent a fraction, because as you make a denominator larger, the value of that number drops. Does that make sense to you? So if I took the number 5, if I divided it by 7, that's probably a bad example. Let's say 35. If I divide that by 7, we're going to get 5, right? If I divide that by 10, we're going to get 3.5. Does that make sense? If I divide it by 35, I'm going to get 1. If I keep going, if I divide it by 70, I get 1/2. So as this number grows, this quantity becomes smaller. Do you see the idea there? So this idea of this division, this is what inversely proportional is all about. It says if y is going down as x is going up, really what we have is y varies inversely, or y equals k, not times. Times would be the direct. Times means as we're multiplying, it's going to go higher. K over, and this is what I talked about yesterday, making sure we knew that direct was k times, because now for inverse we're going to have k over. So when you see the word direct, we mean k times. When we say the word inverse, we mean k over. And this is the reason why. As x is getting larger, this k, that's a constant again. Constant variation, that's not changing. This quantity altogether will get smaller, just like this example I showed you. So again, k is a constant. That's not changing. Let's see if we can wrap this around an example, then do a word problem similar to this one, and we'll be done with our section here today. Okay, so let's suppose y varies inversely as x. Suppose y varies inversely as x. Right now, we know that that's telling us which equation to use. It's either going to be k times or k over, depending on whether we're direct or we're inverse. In our case, are we direct or inverse? So are we k times, ladies and gentlemen, or k over? Definitely. Okay, now we're going to fill out the rest of this. Y is 6 when x is 3. Well, that's going to be important in just a bit. What we're going to try to do is find k and again set up the equation. So find k and write the inverse variation equation. So read through a problem one more time. Suppose y varies inversely as x. We're not dealing with direct right now. We're not k times. We're going to be k over. We just talked about that. So when we set up our problem, which letter is going to come first in our case, y or x? Y. Yeah, that's right. Because when we're looking at this direct and inverse variation, whatever's varying directly or varying inversely as the other thing, that comes first. So if y is varying inversely as x, the y comes first in our equation. It says y equals, and then we have to realize that inversely means, well, that's k over. So we're going to write y equals k over x. This really says the same thing as y varies inversely as x. That's all it means. What do we do now? Yeah, same thing we just did, right? Same exact thing. So when we plug these in or substitute them in, how much is y for us? What's that say?
6.
So 6 doesn't change. How about the k? Do we change the k right now? No, that's what we're really looking for. So k stays there, and over,
33.
oh boy, how do we solve for that? Good, yeah. This is k divided by 3, right? How do you get rid of divided by 3? What's the inverse operation? Let's multiply. As long as you're doing it on both sides, you can do almost anything to an equation. So we're going to choose to multiply by 3. Or if you really want to think about it like this, you're multiplying by 3 over 1, right? Multiplying fractions like that. That means you can simplify them as you go. And on the left-hand side, we'll multiply by 3. So what's k equal to then? Sure. Yeah, we'll do the 3 times the 6. We'll get, these 3's are gone, leaving us with the k. That's what we wanted to have happen there. 18 equals k. K equals 18. Are we going to stop there? We're almost done. One little step. What do we do now? Okay, good. So writing the equation simply means you're going to look back at the first equation you've written and just substitute that k, the value of k, in for k. So in our problem here, we should have y equals, instead of k, we're going to have 18. We're still going to have x. Let's go one step further. If I asked you to find y when x is 2, could you do it? Yeah, sure, the problems in your homework are going to ask you for that. Say, okay, great, you made this up. Now find y when x is 2. How much would y be when x is 2? Yeah, good, it'd be 9. 18 divided by 2, you get 9 out of that. Or find y when x is like 7. Well, then you're going to get a decimal, or you're going to leave it as a fraction. No problem. As long as we're understanding that we make this up first, and then we use this with any information I give you to solve the problem. That's really the idea. And this is going to translate to the next problem we do, which is a word problem. Okay. Let's say you're driving down the road, right? Do you guys ever drive?
Yeah.
You know what drive? Okay, good. So we all have this in common. We're all drivers. Which is scary sharing the road with some of you, got to be honest. I don't ever see any of you, but I had a student one time. I swear every day I would go to school. I'd be driving along. I'd drive my 72 miles an hour because I don't want to get tickets. Put on cruise control. You know, have a nice day. Every single day, she'd go wham, and she would pass me like a bloated. And she was in this big SUV. It was like an Escalade or something, and I could feel like the rumble coming, and she would just pass me. And she'd get to school, obviously, just like Tuesday. I think she had a class before the class I taught her. So she'd get here a little bit before me to go to her class, and I'd spend my hour going here and going to class, and I'd see her, and I'd always give her a hard time about it. But the point is that we went the same distance, right?
Yeah.
We went the same distance. Who did it take longer to get here? We came from the same spot, by the way. She lived right down the street from me. So we lived like maybe a quarter of a mile away, and we came to the same exact spot. Who did it take longer to get here, me or her?
You?
Of course, why?
Did you go the speed limit?
I was going slower, yeah, I was going above the speed. Okay, you need to know the speed limit's not actually 72, man. You're gonna be okay, so yeah, it took me, of course it took me longer. The limit is how fast my car can go, obviously. So it took me longer to get here because I was going slower, or it took her shorter to get here because she was going faster. Does that make sense? In other words, the time it takes you to get somewhere is inversely proportional to the speed in which you're going. Right? So the faster you're going, the shorter it's going to take to get there, or the slower you're going, the longer it's going to take to get there. That's an inverse variation problem right there. So we're going to say this: the speed needed to travel a certain distance is inversely proportional to the time the distance can be driven. Or inversely, let's leave it at time. So the speed needed to travel a certain distance. So the distance is not something that's changing here. We're going the same distance. Me and the student of mine, we're going the same exact distance. The speed needed to travel a certain distance is inversely proportional to the time. Let's spell that wrong. Hey, is that inversely proportional throwing you off, or is that okay with you? Just like directly proportional and varies directly in the same thing, varies inversely, inversely proportional, same thing. Speed needed to travel a certain distance is inversely proportional to the time. Let's say this. The distance can be driven in 5 hours at a rate of 24 miles an hour. That's really slow. Let's make it faster than that. Let's make it like 70. Hours at 70 miles an hour. That's me. Let's see how fast you would have to go to make the same trip in 4 hours. You have to go significantly faster. So you're like, okay, I usually drive down to LA, it takes me 5 hours to get there if I go 70. Now let's say I need to make it down there in 4 hours. How fast am I have to push my car? How many tickets am I going to get, basically? So, how fast do you have to go to make the same trip in 4 hours? Well, guess what? This problem is exactly the same as this problem. Same thing. It's only we don't have y and x. I haven't said that. I've told you something else. It is a word problem, sure. But it's kind of in a nice format. It says something varies somehow as something else. It's going to be something, in this case, what's our first something?
Speed.
The speed. That's what's varying. And it's varying how? I'm sorry, varying how? Inversely or directly?
Inversely.
Varies inversely according to what? Yeah, speed, blah, 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 inversely proportional to the time. So instead of y and x, we have speed and time. We're not going to do the distance because the distance isn't changing. That was just part of the problem that says you're going a certain distance, all right? The speed needed to travel a certain distance. The speed is inversely proportional to the time. Let's set up our equation first. So first thing we got to have is either varies directly or varies inversely, depending on what it says here. Now, of course, we just talked about this is inversely, so can you tell me what equation I'm going to have? Is it k times or k over? Which one?
K over.
Great, so tell me what I should write. Perfect. Do you have some numbers you can plug into that? Yeah, of course, right? The second sentence has to give you something. Does it give you a speed? What's your speed? What's your k? Okay, k is k, we don't know. What's our time? So speed was 70, k, that's what we're looking for, and time was 5. Can you solve for k in this case? How? Yeah, let's do that. So just like before, we'll multiply both sides by whatever's on our denominator here. We learned how to simplify those fractions a while back. K equals what now? Perfect. 350. Are we done? Are we going to have to travel 350 miles an hour to make it there in 4 hours? No, probably not. We've just kind of set up our problem now. We've just managed to find K. What are we going to do with that K, ladies and gentlemen? Okay, so what's the next thing I should write for this? Okay. Perfect. So I am just taking that K, oops, I wrote it right. I'm just taking that K and substituting that into my original inversely proportional or varies inversely equation. The next thing you do, you look to answer that final question. How fast must you go to make the same trip in 4 hours? So the question is, where's the 4 go? Yeah, notice how you have to do this before you answer that question. You got to have this down, right, somewhere. That way you can plug something into it to solve it. So, I'm sorry, where'd the 4 go? T. Good. It's not a speed, right? It's a time. So the speed you need is 350 divided by 4. What is 350 divided by 4? Ooh, you're cooking. 87.5 what? Yeah, it's not a radio station, right? This is miles per hour. And remember, that's an average speed. So chances are if you hit traffic, you're going to have to go even faster sooner. You can really push your car. Isn't this fun? Oh, we're talking about speeding and stuff? Yeah, don't do that, by the way. I don't want to get in jail, like sued for telling you to go 87.5 miles an hour, okay? But that's how fast you would have to go to make that same trip in an hour less time. So in 4 hours versus 5. One other thing, if I said now, instead of how fast must you go to make the same trip in 4 hours, if I asked you this, let's say now you're going 90 miles per hour. Could I ask you how long it's going to take you? I could. Now notice this is going to be your variable. You would have to multiply by t on both sides and then divide by your speed. So you could also do that. That's, I think, an exercise I'm leave to you for your homework. How many people understood what we talked about today? Feel okay about this? Good. So directly k times, inversely k over. We set up our problems, we make our equation, and then we use that to solve.